First of all, thank you for joining us, Bastian. Bastian is an architect and design researcher based in London and Berlin. Is that a commute for you? Where are you at the moment, Bastian? Are you in?
I'm actually sitting in Bavaria.
You're in Bavaria.
I'm at the moment Berlin based.
Berlin.
Yeah.
Okay, so Sebastian has a BA in architecture from the University of Arts in Munich, an architectural engineering diploma from Berlin University of Arts, and has also worked, amongst other things, you've worked with Heatherwick Studio on parametric design, facades, and those are what my notes tell me, and I'm pretty sure even more extensive portfolio than that. The reason we invited Bastian today, and the reason he was a very popular choice amongst the members of the HBBE, is because his column project is probably one of the most, I think, important design projects in our field at the moment anyway. It's one of the very few to address the issues of biotechnology directly and to think about the scale up of biotechnologies, which is something that we're really interested in. So we think it's a key milestone, really. Now, I'm not going to give away too much because I guess, Bastian, you might well be talking about it a little bit in your project now. So if I can invite you to share your screen, Bastian, and I can give you the floor.
Yes, thank you. So is that working?
That's working fantastically, thanks.
Okay, great. So, thanks for the really nice introduction, and of course, I feel really honored to be here today at the BBE 21. Thanks Jane and Martin for the invitation, and I've been following the work of the Hub since you guys started, and I really think it's an incredible setup you got there, and I'm super excited about the future developments. Also now seeing what new projects you're starting and everything. So yeah, I'm really curious how they will develop in the future. Yes, as you said, I'm a trained architect, and currently I'm co-leading a research group called Weaving at Humboldt University's Cluster of Excellence called Matters of Activity in Berlin. And I always feel that it's important to mention that my background is architecture, because in the work we're doing, or in this specific field of research, disciplinary boundaries almost vanish, but it's always quite nice to actually know where one comes from, or which discipline one comes from. So and also I think choosing a title for a talk is always very tricky. So I came up with negotiating structure, and I hope I can kind of unfold what I would like to allude to with this title during my talk. So as you already said, Martin, I will talk about a project I developed together with my friend and former colleague, Daniel Suarez. It's a column, to be precise, a knitted column. And before I'm diving into the technicalities of the project, I would like to elaborate very quickly the scope of the project. So we often get asked what this project actually is, as in, can you commercialize it? Can you commercialize the material? Is it a product like some kind of an umbrella stand? I think someone asked me once. Or can you build a high-rise with it? And I mean, the answer is maybe yes, but it's probably the most cumbersome way to make an umbrella stand, if you know what I mean, and you probably also wouldn't want to see the price tag of this. So, but I mean, besides thinking about the direct application or commercialization, our intentions for this project were really slightly different. So more than investigating only a new building material, we were interested in workflows and interfaces which cross disciplines as well as scales. So it is, if you will, a case study how the fields of textiles, computation, craft, and and biology can somehow come together. And we by no means claim we found an ultimate solution here, but what was really more important to us that we actually found a way to make this happen, or to make it work. And at the same time, actually more questions emerged than being answered. So for this specific project, we were aiming for a design pipeline starting from the nano all the way to the mesoscale. So I would like to unfold this concept in my presentation, kind of working my way up the scales, if you will. So starting from nano to the micro level, and starting, of course, with the scale of microbiology. But first of all, I would like to outline why I think working in this context, microbiology and textiles are quite a good match. So first, from a geometric point of view, a lot of biomaterials are either grown as planar sheet materials, if we think of bacterial cellulose, or volumetric bulk substrate, such as mycelium bricks. And we always have the challenge working with biomaterials to somehow go into the third dimension. So hereby, I think textiles really offer a very versatile and or cater for very versatile spatial and directional configurations. And especially knitting as a special type of textile construction caught our attention, as with only one technique and a rather simple setup, we can achieve a very wide range of different geometries and structures. So unlike other textile techniques like weaving or braiding, we can achieve a structure with only one yarn through manipulation of its geometry. Hereby, the topology of the yarn remains constant while only its geometry changes. Another topic that interested us was what we refer to as yarn augmentation. I will talk about this in more detail at a later stage. So moving away from the geometry part, I would like to draw the attention to biology and the notion of the microbiome, which was similarly important to the project and was also widely, I guess, discussed yesterday. So for this project, I was referring to Burgess' definition of a microbiome from 1988, where he outlines it as a characteristic microbial community occupying a reasonably well-defined habitat which has distinct physiochemical properties. The term thus not only refers to the microorganisms involved, but also encompasses their theater of activity. Yeah, what I actually specifically like about this definition is the use of the term theater. Which I find particularly fitting looking at this rather simple experiment. What we can see on this slide is just a very simple off-the-shelf piece of jute thread put on a nutrient-rich agar medium at room temperature. But this is an experiment which shows quite nicely what we refer to as the textile microbiome, basically the distinct microbial, if we stick to Burge theater, occurring on a textile medium. So textiles actually inherently carry millions of active or dormant microorganisms and spores. And almost every textile comes with a distinct, if you will, sleeping biological activity, which starts to proliferate once it is placed in the right conditions. So this activity depends on the specific type of fiber, its capacity to store moisture, the accessible nutrients in their direct environment, and of course, the distinct metabolism of the microorganism itself. And what I think is really important to highlight here is the role of the environment in this equation. So these biological structures emerge only if energy and chemical levels of the direct environment are, or basically hit the sweet spot, so to say. But usually these active or dormant microorganisms are causing hygienic or even pathogenic concerns. So for this reason, most of the research in the field is actually looking into means how to make textiles antimicrobial. However, such a property could also be seen, in my opinion, as a design opportunity, basically fostering a certain type of microorganism which inhabits the textile and work with their properties, basically. So the basic and looking back, my maybe slightly naive idea was to coat a yarn with a distinct microbiome, which alters then the global behavior of the textile once assembled into a bigger structure through the microbiological activity. And I want to quickly do a quick excursus. And for those who are in the field of textiles, you know about the extensive discourse around functional textiles and wearables. So we had a big wave of wearable tech, which mainly relies on soft electronic circuitry and sensors. However, they kind of still operate on conventional electronics in a rather deterministic manner. So with this project and this aim to actually work with fibers and biology, we really tried to work with a paradigm of microbiology, which has, as you will see shortly, also, of course, hurdles and to overcome and causing things to go wrong, and it's inherently tricky. But really our goal was to a certain extent work with a distinct metabolism of a microorganism to achieve a certain property or reaction. So coming back to the three images of the thread I showed earlier on, and the role of the immediate environment, we can really notice a fundamental difference. Whereas electronic systems operate with what one could understand as closed loop system, meaning they can mostly operate independent of the environment. The setup I'm describing here is absolutely dependent on the immediate physiochemical environment. And in my opinion, this really changes the role of the designer fundamentally, as we have to either anticipate or also create this immediate physiochemical environment. This brings me back to the role of textiles again. Natural fibers generally present quite good conditions for microorganisms to propagate. What we see on the slide is a magnified cotton thread. And natural fibers consist mostly of fibrous cellulose, a natural polymer, and usually have very intricate microstructures, as we can see in this image. Their surface area and the entanglement of the fibers, they create buffer zones as well as deposition areas for or zones of humidity or nutrients. We can almost understand them as kind of sponges, or, like, as I said, buffer zones. The experiment I'm going to present employs the bacterium which Mang also extensively discussed. It's called S. pastori. This is a naturally occurring strain which can be actually found in soil, and it has the ability to precipitate calcite and hence solidifying the medium it is propagating in. And I'm really, really grateful that Mang explained this biochemical process in detail and much better than I could in the previous talk already. So I'm skipping that at this stage. Very handy. But what I think it's important conceptually to understand that this is different to biological growth. So in this case, bacteria is involved in a biochemical process which leads to the deposition of calcite. And what I also find important to note is that the bacteria actually, that is kind of in terms of the material outcome, it is quite important that the bacteria adheres to the specific medium to locally trigger the calcification. At least that's what we found in our tests. So coming back to this initial idea to change the medium to work with textiles, we actually had to kind of ask the bacteria to consider another medium to basically move house. And in some initial tests, we actually could demonstrate that this process also works with a textile medium. So yeah, actually they were willing to move house. The bacteria successfully adhered to the natural fibers. And these are what you see on the slide, some initial experiments. This is another experiment where we also triggered this calcification within a textile medium. At the same time, we could also demonstrate that we could repeat this process multiple times and increase the calcite deposition within the textile medium, what you can see on the right side. So the white stuff is calcite, and as you can imagine, the more calcite build-up we have on a micro level, the stiffer the medium actually gets, the stronger the material gets. And I was really happy that for the following experiments, I was able to partner with a commercially operating geoengineering company in France called Soletage Bachy. And this really enabled me to also put larger scale prototypes to the test and really work on a different scale. Of course, it was really hard to find or to anticipate the behavior of the material. So as there was not really a reference value for such a material, we did some compression testing. And I have to say that, of course, we tried our best to really understand the material, but it is by no means absolutely homogeneous material. So we have local variations. So we try to find some kind of a middle value here. But the interesting thing, what we found with these tests, is that the permeability of the textile really influenced, which is of course influenced by the geometry and the density of the fiber architecture, was a really important parameter. So this parameter then basically became the driver for our material design. And as we found some really nice configurations which worked well, which also delivered the strength we needed, we decided to scale up. And as you know, scaling up always brings in a different kind of complexity, and I guess especially working with biology and biotechnology is quite tricky, and you're probably familiar with. So in terms of fabrication, the idea was to use those findings we got from the initial experiments and to manufacture a continuous yarn with varying diameters and a total length of around 450 meters. So every 100 meters or so, the diameter of this continuous yarn would slightly decrease. And as the piece would be knitted with one continuous yarn in one single knitting process, this actually allowed us to calculate the material, basically to allocate more material on the bottom of the structure, basically when we start knitting, and reduce the material on the top, which would account for around 28% of raw material savings, which is actually quite a lot. So after a lot of trial and error, we found a way to manufacture this yarn in a continuous go or continuous manner. And we also, as I said, this project is really a collaborative effort of the various institutions and people working together. We found a great institution who supported us. It's called the Canet de Mar Textile Research Center. And what you can see here is a rather simple and old technique called lace weaving. And it basically bundles the fibers together with a textile sleeve. This wasn't the tricky part. The tricky part was to really get the tension right and to maintain the permeability, as well as being able to knit with the material. in this diagram, you see how the continuous manufacturing works. So the individual threads, which you see on the left, get bundled and wrapped in the sleeving material, or the red part on the right, and basically combined in the middle, the weaving machine. So to change the diameter, we can simply cut specific threads or introduce new threads to increase the diameter again. So what we ended up with was this pile of material, and even though that we have individual spools, this is actually one continuous yarn, and with a varying diameter between 4 to 10 millimeters, I would say. So now that we finished the material production, I would like to continue to geometry. We were quite fascinated with these simple knitting devices you see on the left, which theoretically allow for an almost endless combination of patterns. And based on the specific yarn allocation and loops, different patterns emerge. And Daniel Soares has researched this really excessively in the project and developed a whole alphabet of knitting patterns. Also, at this point, I would quickly like to talk about methods of scaling up when it comes to textiles. Usually when we think of textiles as, or we think of textiles as membrane structures, they're usually scaled by increasing the area of fabric, which means only the area increases while the yarn diameter remains constant. What we have here is rather unconventional. We scaled both the textile structure as well as the yarn diameter. This is quite interesting on multiple levels, I think. First of all, sorry, I'm having some, this is okay. So, so first of all, we achieve a fundamentally different structural system. So instead of dealing with a membrane structure, as I just mentioned, we end up with something which resembles more a space frame, I would say, assuming, of course, that the structure gets solidified. And secondly, the increased diameter presents a whole new design space, in a way, a yarn architecture in itself or by itself. So, okay. So what this slide shows is that the patterns react differently to tensile forces. This is a great diagram made by Daniel. Daniel also extracted their logic and included it into a digital model to see how the patterns would behave. So we tried a lot of different knit patterns, which we evaluated in regards how they behave under tension. So the idea was generally to tense these structures, and so they would settle into a tense geometry, and in a secondary step solidify the structure. What we looked for were patterns which on the one hand resulted in some kind of cross bracing, and on the other hand developed a certain structural depth. So this simulation, which served as an approximation to determine the tense geometry of a specific pattern. So on the one hand, we tried to do this computationally, but on the other hand, we also investigated the behavior and the tension with a lot of small scale physical testing. And we kind of tried to find the middle ground, because of course, we on both sides, we had some a certain amount of how can I say that, a reduction in complexity. So we really had to think, how can we tackle it? How can we get this under control from a simulation side? And as you see, the change in geometry and in geometry and size mostly is due to the individual patterns of the sample. Okay. Yeah, I think if there's any structural engineers in the audience, please close your eyes for a second. This is quite rough. So what we have here is really a rather rough visualization or approximation, and really not an accurate representation of the actual forces. However, this really helped us to determine the rough size of the structure and the structurally critical areas. It also shows the quite unconventional structural transformation of the system. So I would like to quickly explain you this. So we start off with a relaxed textile tube on the left. We then tense the structure. It elongates slightly and settles into a specific shape. Until this point, we understand this structural system still as kind of a membrane structure. At least that's how we simulated it. In the third picto, the structure is solidified and the substructure is removed. What changes now is that the system is now in a completely different load case. So we're now talking about a compressive load. Sorry, my screen has some issues here. And yes, and the solidified, the third image actually shows the solidified substructure, and then the substructure will get removed. So as I said, the structure is now under compressive load, and one can understand actually this moment as the structure becoming a column, what we actually tried. So the concept of yarn architecture and yarn augmentation comes into play again here quite nicely. It is because it's quite clear that the structure will experience increased loads towards the bottom. We react to that first with different knit patterns, as well as the material gradient I explained earlier on. So I would like to continue after these intensive initial geometric studies and the material production with the process of knitting. Before I dive into the knitting process, which was mainly led by Daniel, I would like to say a word about how the installation was conceived. So the installation was designed to accommodate both processes. Its modular construction could be transformed into a knitting loom, what you see on the left side, and into a bioreactor seen on the right side. We also designed a specific loom which allowed us to work with our material in a more efficient way. So really the general idea here was to employ a very traditional craft, but informing it with the input we received from our digital simulation. This is how the knitting setup looks like. You can see it's a really handy working platform, so to say. What you see here is what's called pegs. Pegs are usually very simple vertical elements which help to hold the yarn in place while knitting. And in our case, they look slightly different and much more complicated. In our case, we really had to customize these pegs as our material only had very little elasticity. We had to counteract this property with the geometry of the pegs. And this is a short clip about the knitting process. You can see Daniel Suarez here knitting these endless courses with one continuous material, as I said, and very different patternings. So it took a while, but it was really nice to see this, like really a method developed from craft to be translated into a final piece. And here's the finished column with the graded material and the graded knitting patterns. As mentioned earlier on, not only does the yarn diameter react to the structural loads, but also the knitting patterns. So on the bottom, we have a very dense pattern and also very thick yarn. In one of the middle sections, we see that the structure gets lighter, so the structure changes, and also the yarn diameter, which is also which you can also tell by the color. So the color indicates the change of yarn diameter. And moving further up, we can see that the structure also gets slimmer, and towards the top, we really have a very, very kind of elegant, very filigrane structure. So after we finished knitting, we were ready for the calcification process, which meant that we had to shift to the other setup shown on the right. We kind of reconfigured the system and integrated this bioreactor I designed. So the way it works is that the bioreactor basically rotates the structure. Basically, the textile structure is mounted into the bioreactor, and the structure rotates and is constantly irrigated with the right amount of bacteria in the first round, and then following in a second go the activation liquid, which consists of calcium chloride and urea. We used this method to use the resources more efficiently. So let me explain this. In the initial small-scale experiments, we were able to fully submerge all the samples in kind of a bacteria bath. This would, however, demand enormous amounts of liquid, as you can imagine, with this large-scale setup. So with a method of sprinkling this structure, we are constantly also recycling the liquid which flows off the structure and reintroduce it to the process. This really enables us to work with a lot less material, and which is also, of course, related to cost and the overall logistic effort, I would say. This is the front view of the empty, front and side view of the empty bioreactor. And what you can see here are the two lines of this irrigation system. And this is the installed column, or the textile structure, still at a pre-tensed state, installed into the bioreactor. So at this stage, it's still soft. Here are some plumbing details. Some more kind of mood shots. And what you can see here in this clip is how the treatment actually works. So for safety reasons, we had to encapsulate the process, but it was very important to us that this process is part of the installation as well. And while we see a lot of biomaterials, I think, actually only presented in their most boring state, basically when they are nicely dried, inactive, and often behind glass, we really wanted to make this process visible and really part of the design. So as a visitor, you get a feeling for the process, how the material changes over time, and other sensory qualities. Like the lovely ammonia smell, or kind of these things, but it's all part of it, and we really wanted to embrace this and make this somehow visible and experienceable. Again, this is this sprinkler array, and what we see here is again how it works. So this is a top view. You can see the structure on the top and the sprinklers. Another set of, another line of sprinklers is in the middle. So in a way, the idea was also to, at some point, because we can, at some point at this stage, manually switch them off and on, that we could also through the treatment introduce a material gradient. We didn't realize it with this demonstrator yet, but this is, of course, a thing we wanted to do in the future. What you see here is the material on the left side before treatment and after treatment. So you see there's a quite significant change of structure and appearance. And if we look at the microscale, we really can see the local deposition of the material, of the calcite. So the bacteria is really here the agent which directs the calcification within the medium. So as the bacteria adheres to the fiber, it triggers the calcification locally and makes the crystals form mainly on the fiber instead of everywhere in the medium. The bacteria, in a sense, triggers the calcite precipitation, but also forms the interface between calcite and textile. And yeah, here are some more images which show this deposition on microscale. So ultimately, this process altered the global behavior of the structure from a soft textile structure into a load-bearing column-like structure. Basically from a tensile structure into a load-bearing structure. This is a very kind of a strange approach, but it worked out in our case. So we really, also due to the fact we engaged with textiles, I think it wouldn't have been possible with any other material. I would like to also present another kind of sidetrack or a continuation of the project. We were very honored when we received the Acadia Autodesk Emerging Research Award for our column project. This gave us a bit of funding and enabled us to continue the work on the process and furthermore develop structure as well as process design. So we wanted to explore a slightly more complex geometry this time. Our plan was to construct some kind of tripod structure. If you look at it, it doesn't really look very complicated, but if you think about knitting it, it gets quite complicated. And using, we wanted to use a similar knitting process and a similar tensing process. So what we have here is the stretching of the structure and how we tensed it. In comparison to the other project, we used a slightly different pattern. And again, credits go to Daniel Soares at this stage. He did all the simulation magic and came up with this new patterning, which is more like a hexagonal grid under tension. So this was also explored both physically and digital using Grasshopper and basically simulation. So again, submerging the whole structure also for this project wasn't an option. So this demanded, because it demanded enormous amounts of liquid. So what we came up with a slightly different setup where we used two membranes. And these two membranes were held in place by sand so that we could really minimize the volume. So, and circulate the liquids in between this membrane. So the red line you see is the membrane, and the dotted area is the sand. And the big dots are the textile. It's kind of a cross section on the left. So this really, as I said, enabled us to submerge the structure completely while keeping the volume of the materials needed to an absolute minimum. This is how the reactor with the membrane looks when it's open, basically under construction. And this is its closed state in my outdoor office, where we, as you can see, we could, through these pipings on the top, we could introduce the liquids we needed to treat the structure. So this is an image photographed in between the two membranes. So basically what you can see here is really this, what we can call targeted material deposition I was talking about earlier on. You really see that the calcite mostly appears on the fibers. We were also interested to locally vary the material deposition, the calcite deposition, and also the other column project would have allowed us to do so. But in this project, we could really realize this much more easy and in a very simple way. We totally applied 3 complete treatment cycles, and to reinforce the lower part of the structure, we applied only we basically applied the 4th treatment only for the bottom part. Basically, we filled it only half. So this resulted, of course, of a reinforcement of the lower section of the structure. This is the unwrapping, which was quite an event. Quite curious. It's more like, it felt like doing archaeology or something. It came out really nicely. It worked surprisingly well, the whole membrane thing, because we didn't really try it. So it's worked on the first go, which was quite nice. And this is how the structure came out. So the new treatment process was really almost 70% more efficient compared to the one applied in the column project. This is due to the fact that we had very long periods where we didn't agitate the medium. So therefore, the process could happen much more efficiently and had much more time to happen. And the process generated a very specific materiality, also in the column project. And what I find really exciting about these structures is the process of making and their multi-layered agency during the making. So starting with a soft handcrafted textile informed by a computational design process, which is then gradually rendered into a rigid compressive structure through bacterially induced calcification. And in a way, all these steps remain readable and perceivable in the final piece. Yes, and also maybe some promotion here on the side. In case someone of you is in Porto these days, the piece is currently on display at the Porto Design Biennale in an exhibition called Museum of Vibrant Matter. So if you're in Porto, go check it out. I want to get back, before I finish my talk, I want to get back to the title. What I wanted to convey with the title was of the talk was the fact that all these processes are very different how we conventionally manufacture building materials. At many stages, we as architects quite literally have to give away control in this case. So rather than imposing forms and shapes onto a material, it is more a form of negotiation with all these different agents which come into play. On the one hand, the biology, on the one hand, the craft and the simulation. So these processes we only to a certain degree can influence, but by no means actually fully control. So I think this is a really interesting part of this. It's sometimes quite tricky to cope with this, but especially also I think textiles offer this opportunity to really guide materials and get to really unexpected results, like in this case. So I would like to end my talk thanking all of our collaborators. As initially stated, these projects are really a collaborative effort. I especially want to credit and thank my former colleague and friend Daniel Soares at this point, and also the many institutions who supported us over the last years. And of course, I also want to promote my current position at the Matters of Activity Cluster of Excellence by the Humboldt University in Berlin. Thank you very much for your attention, and I'm really looking forward to take some questions. Thank you.
Thank you so much, Bastian. That was a fantastic presentation. And given the amount of activity going on in the chat, we need all of the time we can get to do the questions. So if I can invite Magda as well to turn on your camera, I believe that we are both sort of co-hosting this now. Yeah, thank you. Magda has been trying to group them together because we've had so many questions. And what I'd encourage you to do, Bastian, is after this is finished, go to the YouTube channel and just check out the comments and inspirational bits and pieces. We're not going to get through everything. I think there are some ways we can catalog the questions. I'm just looking at Magda, your proposal. I wonder whether you wanted to, so I think there are a bunch of questions about access to the knitting patterns and where you might have published. Maybe that would be a good start or end. Are there any papers that you worked on or are working on, or sources of things that people can go to or should know about to follow the work that you've done?
So at first, I really want to say that I have to credit for most of the knitting part my colleague Daniel, and he is currently also doing a PhD in this field. So this is not, most of it is not completely published. We do have 1 or 2 papers out which kind of describe it, but of course, this is still a bit, until I guess Daniel finishes his PhD, still in the making. We're of course planning some more publications, but at this stage, not really. In some of our publications, we describe the individual patterns we used here, but really it was a very iterative way, and also finding the right resources. And we are also, I mean, it's the literature about knitting. It's quite interesting. On the one hand, it's very technical. On the other hand, we have a very huge community of people who practice craft, and a lot of grandmas. I think Daniel also often referred to his grandmother knitting and watching her. And so there's this interesting mix of knowledge exchange. On the one hand, very technical. On the one hand, really this tradition of knitting.
Fantastic. I think so. I mean, and is your PhD available now, Bastian? Is that something that can be accessed via the RCA, or is it published in that way?
Yes, I think it should be, how would you call it, disembargoed? Yeah. Because I was working with this commercial company on it. We had to kind of keep cut some stuff due to IP, and but I think it's now available on the RCA research repository.
Right, that would be a very useful source, particularly for our
I can
PhD.
Also distribute it if someone is interested. Just drop me a line. I can send it around.
We'll ask the questions. So we've got so we're at 14 questions at this point. So we can batch them together a little bit. So
I think I really have to
yeah, you may have to go back. But Magda, you kind of grouped them together pretty logically. So there is a series of questions really about the use of this physics simulation and structural performance. Do you want to pick up on these, Magda? The particular ones related to structure and the way it's modeled, or
yeah. So thank you, Bastian. That has been very, very interesting presentation. So there is a question about whether you used a proprietary software, or you developed your own programs for physics simulations and visualization. And then there is another group of questions for the structural performance, which I can ask you later.
Okay, so no, we actually used the basic Kangaroo tools for the simulation, and as I said, it's really was a rough approximation, because the material testing I did gave us we had really large fluctuations in terms of, because it was a process we just were about to develop, and we kind of tried to directly feed it in to the simulations, and we had. It wasn't super, I mean, it wasn't a really precise simulation, I would say. However, it really helped us to, in a way, understand the logic of it, or the fundamentals, so that we can really move forward, and that we had some kind of security that the system would then hold together in one piece and wouldn't directly collapse. So we tried with this to vaguely approximate the structural loads we will anticipate, but we couldn't at this stage really calculate the whole structure through, because it was also, I think there's not a lot of work done, especially if we look at what we did with the yarn, basically scaling it up. And there's a lot of work on membranes and textiles and how to simulate them. However, I think the concept really changes as soon as you scale up the thread, because you have like almost like tiny sticks, and you try to approximate this, or like tackle it by in a way trying to reduce it to a structural system, as I said, which is more close to a space frame, if that makes sense.
Okay, thank you. So there is a list of questions about the structural performance. So if I may start, when you talk about the load, do you mean its own weight, or you actually added static or dynamic load on the top of the column? Do you want me to continue with the list of questions about the structural performance, or just?
Yeah, I mean, I think there's a lot about, I mean, I guess to summarize the questions, and there are a number of them that you might want to answer in the chat, actually, that are kind of more detailed. But the idea is what structural load you were modeling for, really. Is it dynamic load? Was there a static load? Or is it actually just the self-weight of the material? Because you're showing that, I mean, essentially the compressor, I assume you wanted it to be a standing structure. That was the aim, not that it was going to be able to hold up a building, for example. But
yeah, so we're really I mean, to be honest, and because you're also quite familiar with how scaling up works in this field, so we really were. There was to be honest, a lot of gambling also involved. Like, we really tried to scale it up, and we could have done it really investigating every step in absolute depth and absolute detail, trying all the parameters. What we really wanted is to demonstrate that we can do it at scale. And for this, we did initial tests. We did rough testing. We knew that we have some values we can work with, and we knew that it with these configurations we were aiming for, it would support the self weight of the structure. And we calculated in some security, and what happened is that actually the target was quite good. So we were on the top of the structure. We were gambling a bit because it was very, very filigrane, and but in a way it turned out to be really, really stiff on the bottom, where we have a lot of material, and where also the flow, that's another thing which we couldn't really anticipate or calculate, is the whole irrigation. So we didn't do any flow modeling, because it wouldn't really, it didn't really give us or it couldn't provide us with the amount of, how can I say, amount of data, or like the important bits and pieces we needed to fully control the whole process. So so in regards to the whole structural testing, it was not the aim to really make an engineering project out of this. It was for us that we had the security that the thing would in the end would stay, that we calculate the right amount of security into the system, and yeah, just to prove the concept. What turned out to work much better was the second project, where we already worked with much denser structures. So the second, the tripod, would really probably support. We didn't try it, but I could stand on it. I think I have the feeling. So it's really incredibly stiff. So this is what I mean. Like the structures are very similar, but the way we treat them, or like the process is operated, it really makes a difference.
It's really interesting. There is a sort of bunch of questions as well about the biology of it, and so again, there's some of them quite detailed and specific. You have now beaten the record for the most number of questions I think we've had in one of these sessions so far, Bastian. So
I see 17. That's
and they're coming as well. They're continuing to come, but I guess there's quite a few questions, and I think this comes from very particular members of the HBBE actually around the biological process. And so we've been challenged with getting nutrients to the bacteria for their survivability, because of course this is not an ideal environment condition for them to be surviving in. We're generally trying to submerge them in the nutrient rather than spraying it on, having it dry out. So I wonder if you could talk a little bit to that process. Is it just to kind of clarify for us, are you seeding the bacteria in there, and then is this a constant process? Are you monitoring the bacteria growth and survivability? Just give us that sense of what the recipe is, if you like, within what you're able to say.
Yeah, absolutely. So the company I was working with, they developed a process where they used actually freeze-dried bacteria. So we would basically rehydrate them, reactivate them, but we're not multiplying them on the structure. So this was kind of more a workaround to really make the proof of concept. We were thinking, we did some initial smaller tests where we were also able to multiply them on a textile medium. However, for the big experiment, we actually used freeze-dried bacteria, which we then sprayed onto the medium. And as I said, we used this. We had, the timing was quite important to that. So we did some tests and trials where we really had to recycle a lot of the liquid that enough of the bacteria will really adhere to the fibers. So we had to almost spray it for, I think, I don't have the exact timings now with me, but it was quite a long time of spraying them and recycling the liquids. And then we had a window of around 6 hours where we had to, in a way, trigger the precipitation. So in a way, that's why I also stated this in the talk, that we're not talking about biological growth in that sense. At the moment, we really have the active bacteria only for a limited time on the structure, and then we're triggering it with the liquid, and then we kind of repeat the process. However, this is kind of almost like an intermediate step. I have the feeling. I think, I mean, ultimately, of course, we also, the whole field talks about living construction and living materials. So the goal, of course, would be to really find a way to supply the bacteria continuously with nutrients, really embed them already in the material, and also extend the span of their activity. And this is a thing we really hope we can also work in the future, or like continue this work.
I can see multiple ways in which that might be approached as well. You can imagine kind of sporulated bacteria within the matrix to start with, and then you kind of enliven them, and there's some really interesting possibilities, I think, there. Magda, you've got sort of a group of around fibers, right? So if you've got those questions.
Yeah, so there are some questions about whether you have considered other yarn production methods to produce more extensible material, or was yarn rigidity a definite requirement? And if different types of fibers were tested, and whether you consider that, whether you think that calcification was successful because of the natural fibers, or it would also adhere to any other type of fibers. And the last one is, where would you see this piece? Like, where would you use this piece of this fabric in the future?
Mm-hmm. So maybe to the first part, I think they're really good questions, actually. The first part with the fibers. So yes, I did quite extensive testing on different fibers, synthetic as well as natural fibers. And what we found is that the surface quality of fibers really matters in this respect. So we tried the synthetic fibers and observed that we almost didn't get any adhesion. So it was really hard to really locate any calcite on the structure. And if we got to a point where we could where we actually could observe some calcite formation, it was really washed off almost instantly. Like it was really kind of peeling off. It was completely different with natural fibers, even though there was also some quality differences. But it seemed that the bacteria was the adhesion of the bacteria to the fibers was much better. So and we traced this back to really the microstructure of the fibers. And now my other colleague I'm currently working with, he also gave me the hint that it might also be related to the charge. But at this stage where we were like 3 years back, we really thought that, or like we're still thinking that the surface morphology, the surface area of the natural fibers, and as I showed in this magnification, like all these kind of tiny cavities, so they really present nice ground for adhesion of the bacteria, and therefore also the calcite formation is quite solid on the fiber. So we really found that the interface, or like the way the calcite formed on the textile was much more adhesive, or like the adhesion was much better than compared to synthetic fibers. And sorry, what was the second question? Please remind me again.
The last one was, where do you see this fabric being used in the future?
Yeah, as I said, like the umbrella stand. I think it's a tricky question. As I said, like the aim was, besides finding or like besides researching new materialities, new processes, was really to see, okay, how from a process point of view, how disciplines and how these different fields could work together, how could they inform each other. So this was really a kind of a technology demonstrator, a proof of concept in itself, so in its own right. In terms of materiality, what we found is that even though the material is really really stiff and almost, as you can imagine, like mineralic, or I don't know if this is the right word in English, but it still has an incredibly high porosity. So there's actually one tiny bit being tested in a coral reef. So because we were thinking, okay, this porosity, this kind of micro cavities might really present a good substrate for further colonization. Like we still see this column not as a final piece. We still, in a way, want to see it ongoing, like the colonization, the override of the structure. Also conceptually, we kind of really tempted to see this as almost like an intermediate step to be introduced in another ecosystem, to what happens also when, as soon as the cellulose degrades, or as soon as the like decomposition kicks in, what actually happens then. So like it's really the idea of not I mean, we would have been happy to have a product out of this, don't get me wrong, but also the aim was to see, okay, how do we perceive time, how does time relate to construction processes, and also this colonization further down the road. Unfortunately, we really haven't we don't have any long-term testing yet, because also the piece got, like, this is a really practical thing. The piece got transported quite from a lot of positions forth and back, and it became more like it's still standing and solid, but I mean the top part gets like it's also like this. It's questioning permanence. Like it's not an absolute permanent structure, and I also don't think it's really good at dynamic loads. But that being said, I think it has some really interesting material properties a normal concrete structure probably wouldn't have, or it would be quite hard to achieve it.
Thank you, Bastian. We're going to have to bring the conversation to an end, even though we're probably only about a quarter of the way through all of the questions that have been asked. I think there were some more general questions as well that it would be maybe nice for you to reflect on in the chat about methods and about this idea of scale up, what your own senses of whether there are underlying methods that you think are important to the world of biodesign as well. Do you want to just, in the last minute or so, just speak to that idea? What do you think are the fundamental things that you have learned about biodesign and the importance of method, and what methods you think are important more generally? And in the last minute or so, it would be great.
Okay. I mean, what I think is incredibly important is the work, or like in a way, almost like the policies around it. So what was incredibly hard is to organize such a project at this scale, because every workshop throws you out. They say, no, you can't do it here. Every gallery doesn't want to have this piece in there, like the process of making it. Every university has health and safety concerns, and no lab has the capacity and the space for such large scale experiments. So I think that's exactly the right approach. Also, you guys are doing. We really need laboratories. We need a new form of workshop where we can do these experiments. So this is like, besides all the material stuff, simulation, biology, I think this is such a fundamental part of infrastructure, which is still missing in our field.
We completely agree. And that is partly why we're trying to do what we're trying to do. Although having given a health and safety briefing to everyone a few days ago, it's still a restriction and a constraint that we need to get around. So thank you so much, Bastian. That was fantastic. As I say, that I've never seen this many questions to any of the sessions or seminars that we've done. We could only get through some of them. I hope we've done some of them justice, but it would be really fantastic if you could go to the YouTube page and in your own leisure, maybe respond to some of the more specific questions with links. I've put the YouTube page in the chat for you, in the Zoom chat, so you can go directly to there. But thank you so much. That was an amazing start.